computing all zeros of harmonic mappings.
Yeah, thanks for the kind introduction, and thanks to the organizers that I get the chance to be here. So my topic is the computation of all zeros of harmonic mappings, and this is joint work with my colleague Olivier Sète from TU Berlin. And just as a brief recall, for us a harmonic mapping is a complex valued function from the plane to the plane, fulfilling Laplacian f is equal to 0. And such a function has a local decomposition into the sum of an analytic and an anti-analytic functions. So, and we have many theoretical results for special classes of functions about the maximum number of zeros, especially for harmonic polynomials and rational harmonic functions. And the latter functions are of particular interest when modeling gravitational lensing, which is a phenomenon in astrophysics. But yeah, even for this application, it's more important to actually compute the zeros and not only know what is the maximum number. And this is our topic for today. So we propose a method to compute all zeros of a given harmonic mapping. And this is kind of a hard problem because the number is usually unknown before. So we're not aware of any problem adapted method for this, and we usually use a continuation approach. So just a toy example here, we see a harmonic polynomial of degree 4, and on the right a phase plot of this polynomial, and the black dots indicate the zeros, and we computed them with our method with a decent computation time and also a good maximal residual. So since the number of zeros is in general unknown, so you cannot easily read off this from the coefficients or so. It looks like a toy problem, but it's probably not. So as I said, it's based on continuation, so the idea is very simple. So assuming that we have all solutions of the equation f of z is equal to eta k, we want to deduce all solutions for the right-hand side eta k plus 1. So very simple. And then we let the eta k's go to 0, and finally we get the zeros of our function. So there are two main problems. The first of all, the number of solutions can change in between. So we see it here, on the right. So the black thick lines are the homotopy curves of our problems. And yeah, as you can see, for the right-hand side eta 0 and eta 1, we have 2 solutions. And for the right-hand side eta 2, we have now 4 solutions. So a pair of solutions appeared as a turning point A. So in general, at turning points or intersection points or bifurcation points, the number of solutions can change. So this is one problem. The other is that to start our procedure, we have to compute all solutions for some right-hand side eta 0. So to get started. And yeah, and we will tackle these problems with studying the caustics and with the harmonic Newton method. So at least what we call the harmonic Newton method. So harmonic mapping is in general not analytic. So we cannot use Newton's method for analytic functions. But of course, it's C infinity from a R2 perspective, and so we can use Newton's method for R2 to R2. And if we then reformulate this in terms of Wirtinger derivatives, we get this iteration. And this looks very good for an analysis in a complex variable spirit. So here appears a g and the h, a g prime and h prime, so exactly what our function is built of. And so it's very useful for us. So and this is not only used to actually compute the zeros, but also to guarantee some convergence properties. So also to analyze this in more detail. So and the other point I mentioned are the so-called caustics. So first of all, a critical point of our mapping is a point where the function is not locally one-to-one. And then we have the set of all critical points, which consists of analytic closed curves and isolated points, and just ignore the isolated points for the moment. So then we have these curves here, and we parameterize them according to the second complex dilatation g prime divided by h prime. So we have a canonical parametrization. So and then we come to the caustics. These are mainly the images of the critical curves. So one can argue the curves of critical values. These are again isolated, has isolated points. We also ignore them. And consists of closed curves, not analytic anymore. So we have these points where the tangent changes by pi, so these cusps. And what's interesting is that the argument change with respect to the parametrization of the critical curves is constant. So this is somewhat apparent in this figure here. So the arrows indicate the orientation, and if we follow one of these caustics, then the curvature is always negative. So since the parametrization of the critical curves is not unit speed, so we cannot say anything about the curvature in general, but about the sign. So this is now very helpful to say something about the number of solutions of equation with a harmonic mapping. So we want to relate the number of solutions for two different right-hand sides. So this will be useful for our continuation method. So we have two non-caustic points, eta 1 and eta 2, and now the following theorem. This means the number of solutions with the right-hand side eta 2 is equal to the number of solutions with the right-hand side eta 1 plus 2 times the relative change of the winding number along the caustics about eta 1 and eta 2. So this seems somewhat complicated. So I have here a figure to explain it. So we see the eta plane where all our etas are located, and we have a single caustic. So here, this is a function f, so doesn't matter. So and we also see the numbers here, 2, 4, and 6, and there they indicate how many solutions our equation f of z is equal to eta have with an eta from the respective region. So with an eta here, I have 2 solutions. With an eta here, I have also 2 solutions. So here, 4, and so on. And so we can now check our theorem. We start with eta 1. It has 4 solutions. So the winding number of the caustic about this point is 0. The winding number about this point is -1. So we get 4 plus 2 times -1 solutions, so 4 solutions. Okay, and if I would move my eta 2 into the region with a 6, then I would get, so then the winding number changes, so we go this way, then we have winding number +1, and we get 4 plus 2 times 1 solutions, so 6 solutions. Okay, and just to mention, I always say, so entering a deltoid-like region gives 2 additional solutions, and entering a cardioid-like region gives 2 fewer solutions. So, and here, I already said, so entering, and so this tends to moving, and here. If we now consider eta as a continuous parameter, I can show you another example. So we have here a harmonic mapping with 3 poles. So displayed on the left, the z-plane with the phase plot of f minus eta, and the zeros of f minus eta are, of course, the solutions of f of z is equal to eta. So the solutions are the black dots, and the poles are the white ones. And so this is the critical curves. And on the right, in the eta plane, we see the caustics, and as again, the number indicating how many solutions I will have. So now I can move my eta through the eta plane. So working something like this. And it has, of course, a dramatical effect to the solutions. So the solution change, and also, of course, the location. And the pole stays the same. Of course, it's just an additive constant. So what we see is that whenever eta crosses one of the caustics, then a pair of solutions appear or disappear at a critical point. And the behavior is somewhat special at the cusp. There, 3 solutions merge together to a single one, or a single one splits into 3. So depending on the direction. And and we will use this behavior for our continuation method. Okay, we assume that our function f has a finite number of zeros. So otherwise computing all zeros would be somewhat an ill-posed problem. And moreover, we assume for simplicity that H and G are rational, so we have a global decomposition. And yeah, now we have our algorithm from some meter perspective. So we start with the initial phase, computing all solutions with some right-hand side eta naught, and then so it's a task to transport this so pre-images of eta naught to actual solutions of actual zeros of our function. So we choose some right-hand sides and then go in a prediction correction loop where from the old solutions we try to construct a set of initial points which is then corrected by the harmonic Newton method, so by Newton's method. And of course we have to handle the case when the number of solutions changes. So then we have to add additional initial points or we have to remove some initial points. So if we have first 2 solutions and then afterwards 4, then I have to put 2 new initial points in. Okay, and I will now explain how to realize all these points. So how to realize initial phase, how to choose the ethers, and how to do the prediction. So starting with the initial phase. So in a punctured neighborhood of a pole, I have a series expansion on F looking like this. So with Laurent series finite principal part. And now we have the following theorem. So if we truncate our function f, so only keep the dominant term here, and as right hand side we have our eta, and then we take the solutions of this equation and use them as initial points for our Newton iteration. Then this iteration will converge to distinct solutions of the equation f of z is equal to eta if eta is sufficiently large. So, okay, I will show you here an example. We see again a phase plot. White dot is a pole, black dot is a solution, and the cross indicate one initial point from this theorem. Now the question is, does this initial point converge to the actual solution? Yeah, we see here below the dynamics of the harmonic Newton map, the sense of attraction. So every point in the plane is colored according to which solution the iteration will converge to with the respective initial point. Okay. So, and we see, we have here the bassin, it's light blue and green and purple. And yeah, the initial points really correspond to the correct bassin. So in this case, eta was large enough. Fine. But then also we have a solution on the very left and also a fourth initial point here. And this comes from interpreting infinity as a pole if it's necessary. So this solution is then somewhat close enough to infinity. So the interesting point is that we have no other solutions if eta is large enough. So this gives a method for the initial phase. So choose eta outside of all caustic points, try the theorem. If this works and I get distinct solution, then I'm fine. If not, increase the eta and go on. Okay, so this gives us the initial phase. Now we come to the transport phase. So now we have to transport our pre-images to actual zeros. Yeah, and the interesting point is, of course, what happens if the number of solution changes? So if the number not changes, then from the local convergence property of Newton's method, everything is clear. So if the eta step is small enough, then it works. So on the right, we first see again an illustration. So here, bassins of attraction again. The darker, the more iteration were required. And so black means no numerical convergence after the given number of steps. So here we have no solution. Here a single one appears, and the single solution splits into 2. And what we now want is to detect these 2 solutions. This is the important point. If we have additional solutions, we want to find them. If we have fewer solutions, we want to know which one to delete. So the strategy is very similar. We again have a special decomposition, which we call the local normal form. This is available for almost all critical points. And then we have again a theorem, C, okay, some C. This corresponds to the direction in which we cross a caustic. And this just means that it's not a cusp. So, okay, and then it's very similar. We have two initial points, and we can guarantee that the method will converge to two solutions of this equation with these initial points. If the delta is small enough, okay, and we adhere a transformation, this just means that the ethers are close enough to each other. So, yeah, and we have similar results for cusps and solutions. So this is only locally, so the other solutions will stay. Okay, so then we have small eta will give, so for small eta it will work for additional or fewer solutions, or if the number of solutions is the same. But the problem is now, of course, yeah, a very small step. Then I have a lot of steps, and yeah, I want to do two large steps to have a have an efficient algorithm in some sense. So we do this greedy divide and conquer approach to choose our ethers. So we have the very first, the eta naught from the initial phase, and the very last is always 0. And then per caustic, which we have to cross, we introduce two ethers. So eta 1 and eta 2 correspond to this crossing here. And yeah, now we try our best. So even if this is a very large step, and if the step fails, and fails mean that we have different initial points converging to the same solution, then we introduce a substep. So just divide them, divide and conquer, and then try it again for the both substeps. And this can, of course, also happen in case of a crossing. So then we have 3 substeps, and yeah, we go on recursively. If it again fails, then we introduce another substep. And yeah, in this way it's guaranteed to work, since we saw in the theorems before, if the eta is small enough, then everything will work. So if the difference between the etas is small enough, then everything will work. Okay. Good. So then our method is somewhat complete. Just recall, we start with an eta naught, choosing this eta naught outside of all caustics, and we try to find then the distinct solution close to the poles. If this is not working, then we increase the eta until it works. This will work, we know this by the theorem. And then we do the transport phase. We choose the etas on this way. So with a greedy divide and conquer approach. Here, and so now I will show you one additional example. This is a function coming from the application of gravitational lensing. So we are computing all zeros of this function of particular interest. And we have here 7 poles, the white dots, and we see the critical curves, and also the caustics, and the monster in between is just a single curve, even if it's not look like a single curve. So this curve corresponds to this one, so the outer critical curve. Okay, and now yeah, we start our method. We want to compute the solutions with the right-hand side eta naught. And so this is the outcome. So first of all, this is the eta naught we computed. Here we have the solution. So I wrote here 8 solutions, but only 7 are visible. So 7 close to the 7 poles. And a further solution is, of course, close to infinity. So we have here a pole. So it should be somewhere here. Yeah, it took us 33 of these Newton iterations. Yeah, now we go on. So we have to move our eta from here to prepare the first crossing. So this gives this here. So this is zoom in. And here also our 8th solution come into play. So we have now 7 close, so somewhat close to the poles, and an additional one on the very left. So this came from here. And yeah, now we cross a caustic, and as I said, if we cross, so we enter a deltoid-like region, then we get two additional solutions at a critical point. They should appear, and okay, we can have a look. So exactly here the two solutions appeared. And yeah, it took us some iteration to achieve this. And then we again go to the next iter. So another zoom in. And the next crossings are somewhat special. So we not cross only a single caustic arc, but two caustic arcs. And so we expect that two pairs of solution appear. So 4 solutions per crossing. And this is exactly the case. So here we have the two new pairs preparing the next crossing. Another 2 pairs appear here and here. And again, now the next crossing gives this solution here and here. And so far, everything went very smooth. So it's a simple idea, and I have no failed iter step. But in the very last step, now, while transporting the solutions for this right-hand side to actual zeros, the method fails. So we're not able to find distinct solutions. So 2 initial points converge to the same solution. Then we have to introduce this intermediate step, and so the first sub-step then again fails, and we again have to introduce another sub-step. And this took us a lot of iterations, also because of we are now having 22 solutions, so this is maybe even not a large number. But finally, it worked, and this is exactly what we expect from the theory. So I showed you already a proof why this will work. And finally, we get all 22 zeros. So this is a known number from the theory of astrophysics, where this function is studied intensively, or functions like this. So we have a maximal residual of order 10 to the minus 16. It took us in some 750 Newton steps, and as you may remember, 400 for the very last step, so bad luck in this case. So the computation time for the transport of images processes, so I think it's decent. It's dominated by the computation time for the caustics. So these are the say characteristic curves. And just to say something about it, these to compute the caustics, we need the critical curves. These are analytic curves, and if H and G are rational, also algebraic curve. So you can choose any method you want to compute these curves. So I do not address this so far. But what's important is that in the application of gravitational lensing, we want to compute solutions with so for one function f for several right-hand sides. So we can use this computation more than a single time. So it's like the LU decomposition or so. Okay, there I showed you the transport of images method to compute all zeros of a harmonic mapping. This is based on this harmonic Newton iteration. So computation, also analysis, and some insights about pre-images under harmonic mappings. The idea is very simple. So we solve f of these equal to eta, and then let eta go to 0. So we have a complete analysis if f and g, if H and G are rational, and our experiments should suggest that it's also working for more general harmonic mappings. So if you are interested, then you may have a look in one of our publications concerning this. And so then thank you very much for your attention.
Adapted to finding nonlinear solutions. It's called the deflated Newton's method. turmeric is quite useful
Okay.
in this context.
Okay. Okay. So I will take this point. So I cannot say anything to it. Yeah.
If I were finding roots of an ordinary polynomial, I wouldn't use Newton's method. I'd use a companion matrix and an eigenvalue problem.
Mm-hmm.
Is there any role for eigenvalue problems here?
This in general works for an arbitrary harmonic mapping. So it has to be a polynomial or so. So it addresses very general function. And I think if you choose something like this, oh, sorry for this. So looking like this, then probably we have some eigenvalue problem you can use. But from the very general perspective, I don't think so.
Well, if I were finding roots of a general function, I would approximate it by a polynomial.
Okay.
And solve a matrix eigenvalue problem. So my question stands. Is there any way to use eigenvalues for these real harmonic polynomials or functions?
Okay, yeah. We actually don't look like that. We only, so.
I have no opinion.
Yeah, okay.
These caustic shapes.
Yeah.
Are there criteria that you have identified when you have an additional parameter? How things can.
How they, oh, yeah. So in physics, they also consider this, and then they call it a caustic metamorphose. So they have a parameter, and then they can change somewhat. But for us, it's only important so that we check how this number of solutions may behave if you change your position with respect to one of these curves.
Yeah, so you have an additional parameter in the problem.
In our
You could, the shapes of the caustics can be critically affected, right? I mean, when you have an additional parameter.
yeah, yeah.
So then you have theorems to tell us how things will change.
To
When you change parameters.
okay. So like no. So you mean when I change slightly my function and then I expect a large change with the caustics also. So to avoid this, no.
Just to say, this could be very useful in wave theory, where the dispersion relation is a fundamental object. That's the relation between the frequency and the wave number. And the very common task is, given the frequency, find all the complex wave numbers. Now, the dispersion relation is often very complicated transcendental function
Okay.
with no convergent Taylor series in any reasonable region.
Okay.
So this could be really
Yeah.
useful. And
So-
it's a real headache doing this sometimes to find all Newton's method. It's so, you need a starting point. And, automating it's almost impossible.
So we proved everything based on the argument principle for harmonic mappings, and so the exceptional points for the argument principle has to be isolated.
Yeah.
So we have to guarantee that say poles do not cluster to infinity. So this might be a problem for some transcendental functions.
Okay.
Well, there are no more questions. Oh, there are no questions.
Wait, there's a question.
I can ask something. Fine.
So there's no question. Okay.